Hello, this is Ken Alonga, and today we're going to look at Lab 7, which is the net force from motion. Today we'll be looking at Python code displaying an orbit around a black hole, and we'll see the effects of gravitational force on orbit with the incorporation of the components of momentum, and our main result would hopefully to be able to gain a greater understanding of the effects of momentum and the relationship between momentum and force. Now we have a look at our code, and we're given some initial conditions. One, we have the star's mass, as you can see right there. Delta T, we're going to use it in a day, so we have the calculations for how many seconds there are in a day. We've uploaded some data from T-square, and now we're going to take a greater look at some more variables. We have here, the calculation of final velocity and initial velocity, which we'll explain more in detail. You also have P initial and P final. For this particular simulation of orbit, we're going to need momentum, and the applications of momentum parallel, momentum perpendicular. First things first, we set up equations in the beginning to calculate Fnet, which is just going to be the same thing as dp/dt, which in other words is also showing the relationship between dp/dt and Fnet. However, the only main differences are that dp/dt is an approximation of the derivative that is used to find Fnet. After that, we can break up Fnet into two different components, Fnet parallel and Fnet perpendicular, or in other words, dp/dt parallel and dp/dt perpendicular. Two of the same coin. Once again, the same differences. Just dp/dt and parallel and perpendicular are approximations of a derivative. As you can see, we took the normal vector because parallel is going to be in the same direction but an increased magnitude, thus explain the differences in mag P final and mag P initial. And once you multiply, you'll have your parallel. dp/dt perpendicular, we easily found that simply just by taking the dp/dt and subtracting it by dp/dt parallel, since dp/dt parallel plus dp/dt perpendicular are the two components which make dp/dt. So we were simply able to get perpendicular. After that, we've set some code so that we have lines simulating parallel and perpendicular. Now if I were to simply run my code, we'll get a better picture of how this orbit will look. And as you can see, the arrows represent the momentum. Perpendicular arrow will force, I guess it was kind of quick, but will force this object to rotate, to actually change direction. And parallel will allow its magnitude either to speed up or to slow down, thus showing more applications of the change in momentum components in terms of parallel and perpendicular. Now, a question was asked: if a black hole of a different mass was placed in the center, and a star were to move in the same position, same motion, would we be able to calculate the mass? And for that question, it'd be almost impossible to tell, simply because if it were to have move in the same direction, we would be missing key components which we use to calculate the mass, which we did by calculating Fnet by the dp/dt parallel and dp/dt perpendicular. Without these crucial components, one would not be able to find mass. So therefore, it'd be almost impossible to derive this information using it. That concludes the lab. Have a nice day.